Good morning, everyone, and welcome to the third lecture of Hacking in C. Today we'll be taking another and closer look at memory. But first, I want to repeat the scheduling change that we already planned. So next week, on Tuesday, the 27th, is King's Day. Now, most of you will probably be aware of this, and even if you weren't, then you probably are now given all the news surrounding certain events that were planned and subsequently cancelled. But the thing about King's Day is it's a holiday, so we can't lecture then. So rather than have no lecture, then a tutorial without a preceding lecture, and then a lecture without a tutorial following it, we're swapping them around. So there is a lecture on Thursday next week, and there will be a tutorial Tuesday, May 11th, so the Tuesday after the May break. This also means that the deadline for the next assignment is Tuesday, May 11th. So not Thursday next week, not Thursday after May 11th, so not Thursday, May 13th, it's Tuesday, May 11th. Okay. So to quickly recap what we saw in the previous two lectures, programs. Oh yeah, let's cover that first. So answers to the assignments. Yes, you will get them. The question is a bit about how we're going to do that. Because so what we used to do when we could lecture on campus was basically the first hour of the practical session, the TA would basically stand in front of the hall and, well, basically explain what we did in that session. But that was back when we had only 80 students. So nowadays it probably wouldn't even work in a physical hall because of the growing numbers. But also, I imagine that just having that as a live session in the morning on Thursday isn't ideal, especially since it now overlaps with the practical still. So I'm thinking about making basically short video recordings where I go through the assignment, or Tom goes through the assignment. So basically for each assignment there will be a short, basically 10-minute, maybe 15-minute video explanation about it. However, to do that for every assignment is a bit much. And also, we can't really set this up for you to answer live questions. So it would be really helpful for this if you would just email us basically some remaining questions that you want to see answered in such a video, and then we can work from there. I mean, there's a few weeks lull in teaching now, so sitting down and just making these videos shouldn't be too much effort. Failing that, like if we actually don't manage to do this, we will just give you the code that works. But I'm hoping that basically everything that needs to be covered will be covered in video. I'm a bit hesitant to just upload answers because so often they won't answer everything. So it will just be, yeah, this works, but there will be no explanation why it works. And other times, I'd rather keep our exact implementation hidden so that we have some material to base some other test assignments off. Okay. So, in the first week, I want to say, but basically I just said, because you've all most of you followed processors, you know how this works. So a program doesn't consist of the code that you type. It consists of machine instructions that operate on values kept in processor registers. And those machine instructions are bytes. Those values are bytes. Those processor registers contain bytes. Everything is just bytes. And the program is basically the semantics about how the machine looks at those bytes and putting the right bytes in the right places at the right time. That's what a program is. Computers really are just rocks that we tricked into thinking. So in C, we have types to give meaning to those bytes, right? And you can convert between those types pretty freely. That's called casting. And then in order to, well, keep track of all that data, we use memory. And if you have these values with multiple bytes, then you get into the issue of endianness. Do you put the least significant byte at the lowest address or the most significant byte at the lowest address in memory? And finally, we saw that C has undefined behavior, which is a class of things you can do that make your program meaningless. So it can do anything, not just something valid in the computer, but it might also format your hard drive or give you nasal demons. Then last week, we took a bit of a closer look at memory. We saw how the 64-bit memory space is laid out. We looked at calling by reference and calling by value, what it really means, and what you basically need for that. We talked about padding values in memory so that they are nicely aligned, like 4 bytes or 8 bytes on a 64-bit machine. And we looked at pointers, where we have this %a operator to get the address of the variable. Oh, haha. Somebody should have said that way earlier. Yeah, I have a list. Just a second. I'm on the wrong output. Maybe I should just scrap this output and never use anything without slides. There it is. So now it's actually relevant for you to see slides. So before now, I was just... I had a running list of what I was saying, but now slides become important. So we have this %a operator that gives you the address of this variable a. And because this is an int pointer, you see, okay, a is probably an integer, right? Because a pointer has a type, and the type of that pointer basically tells you the type of the variable that it points to. So a pointer now contains the address of a, and if you dereference it, then basically the machine knows, okay, I have to go to a, or rather I have to go to that address, read 4 bytes, depending on what exactly an int is on this machine, but let's say 4 bytes, read 4 bytes, and put that in a, well, basically in a register, and that is then a. We saw that you can have pointers to pointers, and you can have pointers to pointers to pointers. It's pointers all the way down. You can do this as much as you like, except, yeah, well, it becomes a bit useless after the third dereference, the third abstraction layer, basically. And finally, we saw pointer arithmetic, where if you add 1 to an int pointer, then the value that's stored there actually goes up by 4 because it goes up by the size of the integer. Okay. Now, we also looked at arrays, which are well, a special type that aren't pointers, but act like pointers in some situations, which there will be an assignment about. To store, well, multiple values of the same type. And finally, we saw strings, which are just null-terminated arrays of bytes. And we saw the fun and terrifying ways in which strings ruin your day. Now, this week, we will look at memory in the broader sense of the memory in the system, in the operating system that your program is working with. Yeah, basically that. And for starters, we're going to look at the stack. Now, I hope most of you know what a stack is. Don't worry if you don't. I'll cover it shortly, but it should have been covered earlier, I think. So let's look at local variables. So imagine we have this program. We include some headers, and we have a main function, and the main function has an integer a, b, and c. And that integer c calls some function, and some function in turn has a local variable, a character array of size 100. Now, these variables are bytes that need to go somewhere. And we want to manage that slightly efficiently. So all the variables on this slide are local variables. And local variables are, well, they have some properties. They are local to the function. So that's why they're called local variables, which basically means they can't be accessed by other functions, bar undefined behavior. But assume for a second that this is true. They can't be accessed by other functions. They are also local to the function call. So by that I mean, if you call the function multiple times, each of those calls has its own copy of those local variables. So if I call function A twice in a row, then those two invocations will have, the second will have new copies of those variables. If I call a function recursively, then each recursive call will get new copies of those variables. So that's important to keep in mind. These are properties that local variables should have, must have, really. And the final property is they only exist during the function call. So as soon as you exit that function, or in the terms of that previous slide, as soon as some function returns, so as soon as some function returns this value 3, then this character array here stops existing. Okay, so how do we do that? Well, what we could do is make every local variable a global variable. So you could just say, okay, we have all this, we have some memory somewhere, and just every function call, for A you point to that those 4 bytes there, and for B you point to those 4 bytes there. That's something you could do, but then you break these isolation properties that were on previous slides, because then every function could access those variables, and if you call the function multiple times, each call would refer back to the same global variable. So to actually make it work, to actually make a global variable of each variable, what you would need to do is, basically solve the halting problem, because what you would have to do is compute the entire call graph, which might be infinitely recursive, you don't know, and create copies for every variable and put that in the global state before the program is ever really run. So this is just not generally possible. Now, there are programs for which this is possible, and sometimes it is done for efficiency reasons. But in general, this is just not how you do this. You'd probably also need lots and lots of space, because every single function call would probably need its own pre-allocated, always present piece of memory. even though it's only there for like 1% of the program's lifetime. So clearly this is not a good option. Okay, what's another option? Well, these global variables have the property that they are pre-allocated. They are made by the compiler, basically, and then loaded into memory when your program runs. So the compiler needs to know about all of them. Your program needs to create all of them when it starts, and then it's not touched during the lifetime of the program. Now, for some systems, this is actually a good model. So I should actually mention this. So for smart cards, something like this actually happens. So for smart cards, because they are basically static memory and one program run for the entire lifetime of the card, all this memory needs to be allocated at the start and never, no freeze and no more allocations can ever happen. So the memory is declared static at the start. But for our programs, that is just not flexible enough. Okay, so can we do better? Well, so for one thing, we have to move to the runtime. So rather than make the compiler do it, we have to make the runtime do it. Let's pretend there is a memory manager, some oracle that we can just ask for some memory when we need it. Okay, so each time we create a variable, let's ask this oracle for some memory and use that for the variable. Okay, but that requires that we would have this code calling the oracle for every function call for every variable. You would need to check, did the oracle actually give me some space, or did she tell me that that no space was available? You would also need to check for arrays whether the memory is actually contiguous, is in one block. You would also need to make sure, probably, that, so suppose the oracle doesn't give you any guarantees about the memory, right? So then you would also need to make sure that the oracle hasn't accidentally given you two blocks that point to the same memory. And you would also need to clean up after yourself every time that you exit a function. That sounds like a lot of work. Now, such a manager does exist, and it actually gives you some guarantees that make it, on most systems, unnecessary to do some of these checks. But those we usually want to use for variables that we want to keep for a longer duration in the program. This is a lot of overhead for things that are very short-lived. However, with function calls, there is a property that we can basically there's a property that we can use to come to our ideal concept of local variable storage. So in most systems in existence, function calls within one single process are like a ladder. You can go up a step on the ladder, you can call a function, and you can go another step up when that function calls another function, and you can go another step up when that function calls another function, and then when that function returns, we take a step down the ladder, and one more step down the ladder, and one more step down the ladder. So that's linearly stepping up and down a ladder, basically. Now, going sideways isn't possible on a single-threaded, single-process view. If you're multi-threading, then you actually have multiple stacks and you are swapping them around, and some of them may point to the same thing in memory, and don't bother with, like multi-threading is way out of scope for this course. So just assume for a minute, going sideways is not possible. We only have this one ladder. We cannot skip rungs. We cannot call two functions at once. And we cannot return two functions at once. And at the bottom of the ladder is the main function. Well, this looks a lot like a stack. So conceptually, a stack is a collection, just like an array is a collection, but an array is a collection with random access. A stack is a collection with two operations. You can push something on the top of the stack and you can pop something from the top of the stack. And you only ever have access to the top of the stack. When you call a function, you just push the local variables on top of the stack. And then you have the memory that those local variables point to, and you can work with that memory. And when that function returns, you just pop those variables from the top of the stack, and then they're gone. And that's all the memory management you need. So when I say here, you only have access to the top of the stack, what I mean is basically you only have access to the memory of this one function that you called that has these 2 or 3 local variables. That memory is the top of the stack. So now you split the responsibilities at compile time because you split the responsibilities between compile time and runtime. Because at compile time, what you can do is, well, figure out for each function, and this is quite trivial, what local variables that function has, and then make some machine code that pushes and pops the right amount of bytes to and from the stack at function call and at function return. Those are different machine instructions for different functions with different variables, right? So 2 functions with 2 integers as variables will probably have the same machine instructions, but a function with 3 integers as variables may have different machine instructions because it has to push a third variable. And then at runtime, all you have to do is keep track of the top of the stack. Because then when you call a function, you run that machine code with that top of the stack you're keeping track of. And you just add those variables to the top of the stack and the stack grows with you. Let's call that thing we're doing at runtime, let's call that the stack pointer. So on the right you see a stack. On the left you see, well, a pretty bare bones example. So main has 2 local variables integers, and func has 2 local variables n and m, which are set to the values of a and b, which are passed by value. So what happens when main calls func the first time? Okay, so on the right side here we have the stack pointer pointing to the top of the stack. The lowest address is here, X is on the lowest address, Y is on the second address. It could be the other way around. The compiler is free to rearrange this. Let's assume that this is the situation. So these 2 variables are the stack frame, as it's called, of main. So when I call func the first time, first thing that happens is, well, enough space for n gets pushed to the stack, and the stack pointer gets increased. Okay. Next thing that happens is enough space for m gets pushed to the stack, and the stack pointer gets increased. And that is then the stack frame for func. Okay, and then n is set to 42, that's this assignment here, and m is set to 23, that's this assignment there. And then the return happens, so n times m gets computed, and the function returns. So when the function returns, those n and m get popped from the stack, and x gets set to 966, and the stack is basically back in our initial state. And when I call func again, the same code gets executed. So again, n gets pushed to the stack, m gets pushed to the stack, n and m are assigned to, and then n times n is computed again, the function returns, so the stack frame is popped, y gets set to the return value, and we have our results in the stack frame of main. That, in a nutshell, is what the stack does for you. That is the most important function of the stack. But we need to put the stack somewhere in memory space. So we have two options there. You'll recall that the memory space on a 64-bit system is, well, conceptually 64 bits, but it is actually 48 bits. Which is divided in kernel space and user space. But it has two ends, right? It has a bottom end, it has a top end. So we can put the stack at the bottom and have it grow upwards into memory, or we can have it at the top and grow downwards into memory. Now, why do we reverse the direction? Well, that is because it has maximum room to grow and it's least wasteful. There is an argument to be made to not reverse the direction and still put it at the top, but these are the two main options in use. Okay, now the architecture we're working on, x86-64, has the stack at the top growing downwards. Remember that, because that is relevant for our attacks later in the course. Now, the other choice isn't necessarily more secure. Possibly even the first attack of this nature was on an upwards growing system. It's just that the attacks work a bit differently on such a system. So we're actually dealing with a downward growing stack, so we have to turn it around. But the operation is exactly the same. So if you have trouble visualizing a downward growing stack, just like turn your paper around, basically. So we're still pushing n and m to the stack when we call a function, and the stack pointer just decreases instead of increases. The memory, well, the bottom address of the stack is actually the highest address in memory. The stack pointer decreases downwards. N and m get assigned to function return, so x gets assigned to. And then func is called again, n and m are pushed, get assigned to, computation happens, function returns, y is assigned to. So the operation I'm showing here is the exact same operation as earlier when we had an upward growing stack. So there was no there was no difference in the abstract operation. Now, where do we put the stack in memory? Where is the top? Well, remember that we have these 6 bytes to represent these addresses. It gets split up into user space and kernel space, and the top half of memory is kernel space on Linux and Windows. So the stack is put at the top of the user space memory, and therefore stack addresses are recognizable because they tend to start with this 0x7FFF, not 0xFFFF, which you would expect if it was really at the top of all memory. So basically your process mostly works with this lower half of the canonical address space. Now, that lower half is still 2 to the 47th bits of address space. You do not have 2 to the 47 or 2 to the 48 bits of physical memory. And you probably also don't have that amount of disk space. So what's going on there is that this is all virtual memory. This address space doesn't really exist. It's a fairy tale that the computer tells your process. And when it's actually needed, when it's actually written to or read from, that's when the computer decides, okay, I need to put it on one of these RAM units, or I need to put it on a disk, or something like that. So it's backed when it's needed. And backing can be in the form of RAM, disk, tape, whatever. Now, some systems actually overcommit memory. So Linux overcommits, Windows doesn't. What does overcommit mean? Well, if you basically tell all the programs that live on the system that there is more memory available, then you would be able to actually back when all the processes use the memory they asked for. So process A asks for 2 gigabytes of memory, process B asks for 2 gigabytes of memory, and your system only has 2 gigabytes of backing in the form of RAM and swap or whatever, then Linux will happily give both those processes 2 gigabytes of memory and just hope they don't use it all. They don't use all the memory they asked for in a way that Linux would have to actually back up the memory, give them the memory they asked for. Whereas Windows will just refuse the second one, even though the first one isn't using all the memory that it asked for yet. So this is a bit like speculating basically on whether or not processes are going to use all the memory they asked for. Okay. So how do these virtual addresses translate to actual memory? Well, clearly, because the virtual address space is so huge and we are putting something at the top of the address space, we can't really let processes use the actual addresses of physical memory, right? Because the addresses that the stack lives in don't exist in my system. I only have 32 gigabytes of memory. That's less than 2 to the 47th byte, so my stack would live nowhere. So instead we use these virtual addresses, and then for each access to a virtual address, the system maps that to an actual physical address. Now obviously we don't want to map this byte by byte, because then that would be very inefficient. So what actually happens is basically typically the system divides the memory into pages of 4 kilobytes, but they can be larger. You can have a gigabyte page. And then you use a so-called page table to establish this mapping. So basically, when I ask for stack space at the top of the memory, then the system says, oh, okay, I have a few megabytes free over here and a few megabytes free over here, and I can pretend that it is one contiguous space for your stack, and we'll map it as we need it. So if your process tries to access a virtual address that it didn't request, then it exits with a so-called segmentation fault. The system will basically tell you there was no memory allocated there, this is not for you. So this way, at least on x86-64 and most systems nowadays, processes are easily isolated from each other because the process only sees this virtual address space for its own process. And the operating system can easily keep track of which memory pages belong to which process. Now, in the rest of this course, we will deal with the virtual address space of an x86-64 system. We will deal with the addresses as the process sees them, not the actual addresses in physical memory, because that would be quite useless. So let's put the stack actually in the entire x86-64 memory space. So on the right side, I have a slightly subdivided version of the user space memory of the x86-64 memory space. Now, don't worry about these lower sections, what they mean yet. We'll go into that. But again, the operation of the stack is just very easy. When func is called, the stack frame of func gets added, the stack pointer gets decreased because that's the direction the stack grows in, and when func returns, the stack frame of func is removed and the stack pointer increases again. Now, the stack I went over earlier was a bit too simplistic, so let's look at a few more things that happen there. So when I call a function, it's not just the local variables that get pushed to the stack. Another thing that may get pushed to the stack is the arguments to the function. So if you recall, func had these arguments a and b, well, there needs to be a space somewhere to make a copy of those arguments. So the caller puts those arguments on the stack. And then, and here's where it becomes interesting, the caller pushes the return address onto the stack. And remember, a program is just machine instructions operating on bytes, right? Those machine instructions are also bytes that live in memory. And most computers nowadays expose themselves as a von Neumann architecture. Even though they're... So you've probably heard of the von Neumann and Harvard architectures as these different architectural ways of building a computer, where the Harvard architecture separates basically the instruction memory and the data memory, whereas the von Neumann architecture treats these as one. Now, computers nowadays, especially like things like Intel and Intel CPUs and ARM CPUs, often actually are kind of a mix of these two because they have like separate ways of fetching data and instructions, but they are still fetched from the same memory. So, the key point is that machine instructions in the von Neumann architecture just also live in this memory. They are in the same memory space. We'll look where in a minute, but they are in this address space. Now we have an instruction pointer register in the CPU that has to keep track of which instruction in that memory space it's currently executing. And each time it executes an instruction, the instruction pointer increments to the next instruction and increments to the next instruction. And when an if statement happens, there's a branch. So the instruction pointer just jumps to the right instruction there. The instruction pointer is also known as the program counter. And importantly for function calls, what they require is jumping somewhere else in the code where the function is. But at the end of the function, they have to jump back to where it came from, right? Because there is a function call somewhere. The instruction pointer jumps to the instruction for that function, but the function itself doesn't know where that jump came from. So there needs to be some bookkeeping to jump back to the right instruction. That's the return address. And that lives on the stack in between the arguments and variables of the function. Then there is some other value that may get pushed, and then the function itself pushes the local variables onto the stack. Okay, so we now have the arguments, we have the return address, we have the local variables, and we have some question marks. What are these question marks? Well, we used to have a frame pointer. And frame pointer is the second pointer here that basically points to, the bottom of the current stack frame. Again, bottom in this case means the highest address because our stack is growing downwards. But let's keep with the concept of a stack. The top of the stack is where you have access to. The bottom of the stack is, up here, right? So we have this frame pointer which points to the bottom of the current stack frame, and that's useful for addressing relative to a stable point. Because you might imagine that, the stack pointer might be changing while the function operates because, I don't know, there is some additional variable created halfway through the function that wasn't that wasn't pushed to the stack yet. And on x86-64, this frame pointer lives in the RBP register. But and if we did a function call in this situation, then this frame pointer would also be saved to the stack. And just like the return address gets put into the instruction pointer register again, the saved frame pointer gets put into the frame pointer register again, right? So it's some additional bookkeeping just to keep track of the position in the stack. But on x86-64, this is commonly omitted because, well, not doing that leads to faster function calls. And not doing that means you have an additional register available. And on a machine where you only have 16 registers to begin with, an additional register can actually speed up code by a lot. And we don't actually need the frame pointer anymore. Compilers have been for a long while smart enough now to just do everything relative to the stack pointer. They don't need the frame pointer anymore. Now you can still turn the frame pointer on by asking your compiler to do so, but it's not necessary. So if it's not turned on, this saved frame pointer won't be there. Okay, so aside from storing local variables, we've seen that on the stack we are also keeping track of function arguments, which we push on the stack before jumping to the function. Just to prevent some surprises there, on x86-64 machines, the arguments, the first 4 or 6 arguments, depending on whether you're on Windows or Linux, are actually passed via processor registers. Because that's faster than pushing them to memory and then reading them from memory again. You just put them in the registers and then they are still there when the function starts executing. This kind of thing is defined by calling convention. Now, fortunately, x86-64 only has 2 real calling conventions in use. The Windows one, where there's only 4 arguments in registers, and the everyone else one, where there's 6 arguments in registers. The x86 architecture, the original 32-bit architecture, has 14 calling conventions in common use. So be glad we're doing this course in 2021 and not 2001. Because you only have to know about this one calling convention that Linux has, and only to prevent surprises at that. Okay. So the stack also keeps track of the return address, which we push on the stack. And when we return from the function, we pop the local variables, we get the return address, we pop the arguments, and we jump back to where we were executing before the function. We can store the return value on the stack, which wasn't on the previous slide. And the reason it wasn't on the previous slide is also by calling convention, the return value is passed by register on x86-64, on ARM v8, and probably many other platforms. Because again, doing this by register just makes a lot of sense. It's faster. There is nothing that can go wrong really, except the things that could go wrong anyway. And well, if you do have a stack that stores the return value, then you would pop the variables, return the get the return address, pop the arguments, push the result, and then jump back. And finally, something else the stack might do if it's turned on, manage the frame pointer, but again, not on x86-64. So I'm getting the question, in the processors course, the CPU we made had 16 registers. How many registers does a typical CPU have? So the x86-64 architecture is actually well defined with a certain number of registers, and there are then extensions to the architecture that add additional registers. I would have to look up the exact number of typical x86-64 CPUs, but it's on the order of like 16 normal registers, and then a bunch of special purpose registers, like extra wide registers or vector registers, things that you can compute in parallel on. But there's not really an answer to give there. Like, different architectures of different eras will have a different number of registers. Also interesting, maybe, but don't let this confuse you too much. So some CPU implementations, even though they have 16 registers, really have way more than that. And something similar to this virtual memory to physical memory mapping is actually going on inside the CPU. It is doing some register remapping to basically backing memory for the registers. Don't worry about that. Don't think that this is that this is exam material. And then somebody is correctly making the comment, some registers are only available running in certain modes. Also, some registers have multiple ways of addressing them, and that basically alters the width of the register. So on x86-64, which one is it? So on x86-64, basically, let's say we have this okay, so we have a register called RAX, which is 8 bytes wide. 1, 2, 3, 4, 5, 6. I never do this right. 7. There we go. Okay, so it's 8 bytes wide. That's RAX. However, you can also access this with the name EAX, and it's 4 bytes wide. And you can also access it with the name AX, and then you only get these 2 bytes. And then you also have I think it's H, and then it's just the 1 byte here. So that's all the same register, but depending on how you use it, you get a different number of bytes. Probably not gonna be relevant for this course for the most part. Oh, it's not fully on screen. There, now it's fully on screen. Okay, so like I just said, RAX, full 8 bytes, EAX, right for most 4 bytes, AX, well, AH, right? So, again, probably not going to be relevant for this course, but interesting to know nonetheless. Okay, and I think we should, yeah, let's first do the stack gotchas. Actually, no, that's long enough. Let's have a break. Break until 11:30, and then we'll continue with everything that can go wrong on the stack. And we're back. Okay, so before the break I said we would look into everything that can go wrong in the stack. This was, of course, a gross exaggeration because the rest of the course can be summed up as some of the things that can go wrong on the stack. So we'll just look at a few things that can go wrong on the stack right now. Okay, so you're probably aware of this handy website, Stack Overflow, where you don't post homework, but you do read some answers. And that website is named for the very real situation of running out of stack space, namely a Stack Overflow. Now, a Stack Overflow in principle isn't too worrying because your program will crash, right? But the stack isn't the only thing in user space memory. There were these other things at the bottom that I didn't really go into yet, but they are there. And the stack grows toward these other things. So you want to limit the stack so that it doesn't grow into the other things, right? So you can have limits set by your operating system or by the hardware, and if you're lucky, you're on a system that prevents things from going seriously wrong. So you can use the rlimit system in Linux, which you can access on the command line via ulimit, to manipulate some of these restrictions, give you more or less stack space or more or less heap space, stuff like that. So on Linux, you have control over these limits, and the system will prevent you from growing too big. Now, if you're unlucky, how bad is wrong exactly? Well, so this is already 8 years ago, but basically there was this case where a Toyota vehicle accelerated out of control, and that led to the death of one of the occupants. And it turned out that this wasn't the error of the vehicle's driver. It turned out that it was actually the engine control module software, the firmware running in that hardware, that was at fault. So what went wrong there? So consider this, right? You are writing a piece of software that controls a car. And a car is a 2,000 kilogram hunk of metal hurtling down highways at 120 miles per hour. 120 kilometers per hour. Basically, it's a murder weapon in disguise. That's a car, right? You're writing software that controls that. So one of the things you can do to make your software more robust is that every variable you basically have it in two separate locations. And every update to such a variable you do to both locations. And when you read the variable, you take it from both locations and you see whether they agree. And if they don't agree, something is seriously wrong and you should shut down the engine and park the car, right? The parking the car will be the driver's responsibility, but basically you should make sure that the car comes to a safe stop at that point. That would be the ideal situation if that happens. Well, Toyota wasn't doing that. They weren't mirroring the variables. Most importantly, the variable target throttle angle wasn't mirrored. Target throttle angle is basically how far have you depressed the gas pedal. Other critical data structures in the operating system also weren't mirrored. And, well, there was a stack overflow. So Toyota analyzed its stack and claimed, well, it will only ever occupy 41% of total memory, so all these unmirrored variables, we can just put them in this other 59% somewhere. And they did that, and then it turned out that the stack was actually using 94% of total memory. And the analysis also concluded that one of the reasons why this happened was that Toyota's analysis just ignored the stack use of about 350 assembly functions. And Toyota used recursion, even though that is absolutely forbidden by the MISRAC guidelines. And those guidelines are basically the Motor Industry Software Reliability Association's guidelines, which basically say, don't do this. You will kill people if you do this. That is the bottom line there. So the conclusion there was a litany of other faults were found in the code, including buffer overflow, unsafe casting, and race conditions between tasks. Now, a race condition in a car may sound like fun, but again, people died here. So yeah, that is how wrong can be. So, common mistakes or bugs caused by stack issues are, well, stack overflow. So you cause them by infinite or at least too deep recursion, or creating too many or too large local variables. Another bug you might run into is that stack variables aren't auto-initialized. Remember, we're just pushing space onto the stack, we don't want to initialize that space because that takes CPU cycles and we don't want to spend those CPU cycles. So that means that if you read stack variables before assigning them a value, what you'll actually get is data that a previous function call put there. What's also pretty important, at least on our von Neumann architecture, is that the stack mixes program data and control data. So it mixes the variables with the address information needed to step through the code, right? The return address is in between the variables, which may become a problem if you write beyond buffers. So if you accidentally or intentionally write to a pointer or an array outside of the bounds of that thing, then you may override frame pointers or return address. You may override some of these control data. Now, in the most benign case, this leads to a segmentation fault if you overrode it with garbage. In the malicious case, if you overrode it with the address of your attacking code, then the program, when the function returns, will see, oh, let's jump to this address, and it jumps right into your code that opens a shell and connects to the attacker system. So yeah, that is what is called a buffer overflow attack, and that is why it works, because you override a return address with some interesting piece of code, with the address of some interesting piece of code that does what you want, rather than what the initial programmer wanted. Okay. Another limitation on the stack is that it cannot preserve data beyond the return of a function. So if I call this function as it says here, so I say, okay, I define an int pointer table 3, and that is the return value of table of 310, right? And a table of function, it allocates an array of length, well, 10 in this case. It fills the array with some numbers, and then it returns table. But then the function returns, and the stack cannot preserve that data beyond the return of the function, because as soon as the function returns, its stack frame is invalid, right? If you call a function again, then the memory that table lived at will be overwritten by that other function. So any data that is on the stack cannot be preserved beyond the return of a function. Of course, you can return a pointer to some memory elsewhere, but memory that's actually on the stack is gone. And the other obvious limitation here is that if I pass it length 4 gigabytes, then this will grow outside of stack bounds. So there's the question, can you also move the stack pointer yourself in C? I think you can if you write inline assembly. So that's not technically writing C, I know, but you can, with inline assembly, just assign values to some other, or to registers. So yes, technically you can move the stack pointer yourself. You probably shouldn't, but you can. Okay, so that's the stack. Now I've mentioned a few times this other memory somewhere, right? Like I said just now, memory can't be preserved beyond the return of a function, so you have some pointer to some memory elsewhere, and that pointer you return, and the memory stays alive. Well, that memory is usually in the heap. And the heap is conceptually very simple. Just think about it as a large piece of scrap paper. And we basically can request continuous space on that piece of paper. Note that continuous in virtual memory again, doesn't have to be continuous in physical memory, but we don't really care about that. Just pretend it's continuous. So that space is accessible through a pointer, and that space remains valid across function calls. So every function that knows a pointer to that space can then use that space. So how do you get access to that memory? Well, there's this handy little function called malloc, and that is basically the function that I was alluding to earlier when I said, well, such an oracle exists and we can request memory from that oracle. Well, malloc is the function you use to ask the runtime, the operating system, for a block of memory. And it's really very simple. You ask it for a number of bytes, and it gives you a pointer to an allocation of that size. Or it returns null. If the memory is not available, if it cannot be allocated, it returns null. Usually pointers in C are typed. You want an int pointer, you want a character pointer, whatever, right? You want malloc to contain 1,000 integers, then you want an int pointer. Well, this void pointer that malloc returns just implicitly casts to whatever you want. So in C, this is valid. You just say int pointer x is malloc of 10,000 times size of integer. So basically this is requesting space for 10,000 integers on the heap, and it gets an integer pointer to that space. Okay. So what about this null? Well, the value null is a bit special. It's really a special signaling value. The value null is guaranteed to not point to a valid address. So it's basically a trap value for addressing. Null is not a valid address. Now it's important to note that null is not the same as 0. It may be internally represented as all zeros, but it might just as well be 0x coffee or 0x dead beef, right? Nothing prescribes that null is represented as all zeros. Now, the following code produces undefined behavior. Define an int pointer x, set that to null, and then try to dereference it. What we're doing there is basically asking the system, give me the value of the bytes that live at this address that is not a valid address. It doesn't have a place to go to. Asking for the dereference of null is undefined. It doesn't have meaning. So never try to dereference null. Now, in order to check whether malloc returned null, in order to check whether you actually have a valid pointer, you can use it in Boolean expressions, because that is defined. In Boolean expressions, null evaluates to false even if it's not internally represented as 0. So in C Boolean expressions, 0 is basically the false and 1 is anything else. So null evaluates as false even though it's not the same as 0. These two lines have the same semantics. X equals null is the same as the inverse Boolean of x, right? And then basically you check whether x is actually a valid pointer, and well, this printf is printed if it's not a valid pointer. Now you should always check for malloc failure. Malloc might return null. You don't want to dereference the null pointer because it's undefined what happens. It might crash. It will probably just crash, but it's not guaranteed to crash. And if it's not guaranteed to crash, then you get security vulnerabilities and other fun stuff. So the correct version of that code would be, well, allocate the table, check if it's null, and if it is null, just exit the program or do something else. Do some error handling, request a smaller table, whatever. Right? If there's not enough memory to work with, then it makes sense to crash. But just, you have to check to return the value of malloc. So the alternative way of writing that that check would be this Boolean behavior that was on the last slide. Okay, so that is requesting memory. So now we have memory. What if we're done with it? Well, you, as the programmer, are also in charge of releasing memory, not just requesting it. So when you don't need it anymore, you call free on the pointer. So X has to be a pointer to memory that you have previously called malloc for. Do I have any idea why the decision was made to make this undefined behavior? I assume, so usually this is the case because different architectures are different enough that it would be at least a terrible pain to ensure defined behavior on one of them. So you could say it always has to crash. It always has to stop execution. But then on embedded systems, that might not be an acceptable failure case. So yeah, I tend to not agree with C. Right? That much should be clear by now. So I'm not going to defend the decision, but they will probably have had their reasons. I just don't think they were good enough. Right, so the typical usage pattern of malloc and free is, well, you malloc some memory, you check whether the memory was actually malloc, you do something with the memory, and then you free it. And these calls to malloc and free can be in different functions. They often are in different functions because that is the way you pass data around between functions. Now, not freeing memory that you malloced earlier is known as a memory leak. And that can be super annoying to debug. Your program will just grow and grow and grow in memory slowly over time, and then at some point, 5 days after starting the web server, it will just crash out of memory. So where's the memory leak? Good luck debugging that. Now sometimes you don't want to free the memory, you just want to grow or shrink it. And there we have a function called realloc. Honestly, I don't see this used very often, but if you have a dynamically growing array, for example, or a dynamically growing collection of something, then you may want to realloc at some point. So realloc takes the original pointer and a new size. And content in the already allocated area is preserved and new space is created at the end of the already allocated area, or cut away at the end. Now, if this call is unable to perform its function, it will also return null. And if its return value is null, then the previously allocated memory is still there. It's not freed, nothing happens to it. So the usage pattern for realloc is not just call realloc. No, you have to call realloc on the original pointer with a new size and put that in a new pointer. Then you check whether the new pointer is null. And if it is null, well, realloc failed. So you may want to just exit, or you may want to free the original the original allocation, or you may want to do some error handling and continue with the original allocation. Either way, you have to do some error handling. And if it's actually succeeded in the realloc, then you reassign X to X new. And then we also have calloc. Now remember that the data on the stack is not initialized. Similarly, memory space allocated with malloc is not initialized. So accesses to that memory are undefined behavior. Now on Linux, the first time you do access fresh alloced memory, it will be all zeros because Linux actually ensures that the new memory it gives your process is zeroed out so that you don't get to read old physically backed memory from other processes. But if you then subsequently free that memory and then call a malloc again that gives you that same memory back, you will read the garbage now that you put in there. That is what usually happens on Linux in this case. So memory allocated with malloc is not initialized. Now, the alternative for that is the function calloc, which is an altogether nicer function than malloc. Because, well, calloc doesn't ask for a number of bytes. Calloc, you ask just for a number of items with a certain size. So you don't have to do this multiplication yourself anymore. Also, the memory that it gives you is initialized to 0. So reading directly from it is defined. So the uses for that, well, call calloc for 1000 size of integers, and if it fails, then you just exit. So you don't have to initialize the integers anymore, and you don't have to do the multiplication here. So you now get all 1000 zeros, basically. Now, why am I saying this about this multiplication? Well, the difference here between this malloc and calloc call is the calloc call asks for, well, a certain number of elements, right? The malloc call has a multiplication. That multiplication can overflow, which may result in a successful allocation, but much less memory than you were expecting. And there's no way from the return value of malloc to check for this. You could separately check for this overflow, but malloc won't tell you that happened, of course, because malloc doesn't actually ever see that this overflow happens. Malloc just sees the smaller number that results from it. So when you then start trying to use that pointer, you will at some point start writing out of bounds. Okay, so heap management. So you are responsible for doing malloc and free, right? Now, free is just called on this pointer, but a pointer is just a memory address with a certain type, right? And it doesn't contain, that pointer itself doesn't contain the information that it was actually a memory space of 1000 of that type, right? So how does free know how much memory actually belongs to that pointer? Well, malloc just needs to write this information somewhere, and the obvious location for that is on the heap. Now, one solution is to maintain a table of all malloc addresses and space that belongs to it. But, well, there's a much easier solution. You just write the information just before the start of the allocated block. So you basically write a number or an end pointer or whatever, and then the pointer of the memory address after that, that is the pointer that malloc actually returns. And then when free is called, it reads that bookkeeping data and does what it has to do. Okay. Now, pitfalls in heap management, because of course there are pitfalls. You should never use a pointer after it has been freed. Malloc x, free x, and then try to dereference x again to see what value is at the first location. You have no guarantee whatsoever that memory has not been reallocated. So reading that memory might leak secrets, writing it might corrupt data. It is simply undefined behavior, don't do it. It is in the vulnerability database as a use after free. So this is a serious issue if you're programming in C, where you are responsible for your memory. And right now I'm dereferencing the pointer, but it's also undefined behavior to even read the pointer's value itself. Even though the pointer value will literally be the same bit representation, in C, doing this is undefined behavior. So I'm getting the question about this previous slide on bookkeeping on the heap. How many bytes do you use for the size number? The implementation takes care of that. I assume usually it will be 8 bytes because that's the size of the address space. But it might be more, it might be less. You as a programmer don't have to care about that. As an attacker you might, but as a programmer, if you're careful about doing your right mallocs and frees, you should never have to care about the number of bytes there. It will be enough. Okay, another thing that might go wrong. Freeing a pointer twice. Now, this is a trivial example because we're literally doing it twice in a row, but it's not always that obvious. You may have pointer aliases, right? Multiple pointers pointing to the same location, and if you free one, that invalidates the other. You might attempt to free the same pointer in different functions and just have a complex code base and have lost track of all the functions in which this happens. Now again, this is undefined behavior. And what may happen here is actually corrupt the memory manager to the point that it returns the same pointer on subsequent mallocs after doing this once. And then if one of those pointers becomes attacker controlled, then that can modify and read the memory of the other pointer, which might actually be a secret. So double free is again a potential security issue. And then finally, well, leaking memory, we've gone over this. Basically, you have to try not to lose the last pointer to a location that you have. Because if you lose the last pointer, then you cannot free anymore. Here I have leaky func, which just returns the number of elements it allocates. So it has this leaked pointer. It calls calloc on that this integer of elements, and if it has successfully allocated, if it has not successfully allocated any elements, it just returns 0. And if it has completed the allocation well, it has successfully allocated that number of elements. So return elements. But this leaked pointer is a local variable to this function. And I'm not returning the leaked pointer, I'm returning an integer, a number. So when this function returns, the leaked pointer is destroyed. And I'm left with this allocation of elements that I cannot free anymore. So that's a memory leak. Okay, so I've covered the stack and the heap. Those are the two most important segments, but there are more. So we have the stack at the top of the memory growing downwards. We have the heap in the middle of user space memory growing upwards. And then there's these three other sections: BSS, data, and code. Well, .text it's actually called. Okay, so the stack is for local variables, the heap is for dynamic memory, and then we have a data segment. And the data segment has global and static uninitialized variables in BSS, and global and static initialized variables in .data. Now, the nice thing about BSS, and that's actually an acronym that you don't have to know, but it stands for block starting symbol. That's like something archaic from the 70s. Basically, because the variables in BSS are uninitialized, the executable on disk that takes space doesn't have to have any initialization values for these variables, right? So all BSS is a table of basically sizes and locations, and that's it. No values. It's also it is basically a space saving mechanism. So some people remember it as better save space. But that is in the data segment. So those are the things that are globally accessible to the program. And then the code segment, that is where the machine instructions are. And possibly constants that you put into the machine, into the code when you compile it. So that is where this von Neumann architecture keeps its executable memory. Now the instruction pointers should point into the code segment. And the rest of the course is about what happens if it doesn't. But yeah, so that is where the instruction pointer points. So what are these global variables? Well, they are declared outside of all functions. So this is outside of a function. It's just immediately after an include statement. I'm defining 3 global variables: a long, a character array, and an integer array. And n and s are initialized to, well, a long and a character array. So those will be in .data. And a is uninitialized, so that will just be in BSS. And because it's uninitialized, instead of taking 256 times 4, so instead of taking a kilobyte, it just takes a few bytes. So typically when the program starts, all these variables from BSS are taken and initialized to 0. Otherwise, you would be able to read what was left there by another process. But accessing them before writing a value there yourself is still undefined behavior. Even though typically it works, it is undefined behavior. Now, some platforms actually have a special non-initialized BSS subsection. So if you know for sure you are going to write to that almost immediately, then you don't even need to have this overhead of initializing it yourself. And well, those platforms, usually they are of the kind where basically you wrote the entire system yourself, so the processors don't have processes don't have secrets from each other anyway, so it's no matter if they can read each other's data. But like I said, the C standard requires that all these are initialized to 0. So reading them without initialization in this non-initialized subsection is undefined behavior. Okay. Static variables. So across function calls, like keeping track of how often the function itself was called. You could do that in a global, but then all the functions would have access to that variable. So if instead you define a static int x in the function, then that keeps its value across function calls, but only the functions itself will have access to that variable. So if it was not declared static here, then this function would always print 0. Because after this increment, the stack frame would, like this variable would live on the stack frame would be unwound, x would be destroyed, and the next time you call f, you get a new fresh copy of x. But because x is static, this initialization happens only once, and x actually lives elsewhere in memory. So each increment to x then just increases that single static variable by 1. So you would get the same behavior if x was global, but then it could also be modified by other functions, and we may not want that. So to wrap up memory, we have the data segment where, well, all the data that exists throughout the whole execution of the program lives. So global variables accessible to every function, and static local variables only accessible to the respective function. Caveat, undefined behavior, where you go look for them and try to access them. We have the stack, where space is allocated automatically. Stack space is automatically removed when you return from a function, but you have a certain risk of overflowing the stack and mishandling values there. And then finally there is the heap, which needs to be requested manually. Your request may be denied and you have to handle that. And you also have to free the memory manually. And there you have risks of memory leaks and double freeze and stuff like that. Okay. So that's all the normal stuff. That is all this is how C works. What if we want to know what is actually there on the stack in binary? Can we read the stack? Well, remember printf. So printf is defined as a function that writes the output under the control of a format string that specifies how subsequent arguments are converted for output. Now, this first argument to printf is always a format string. So, what does the following program do? It's just a main function, and all it does is print its first argument. Let me see if I have a version of that I can compile. Yes, I do. Okay, terminal. Where's my terminal? There's my terminal. Okay, so here's this function. Just main print its first argument. So GCC minus W all minus W extra minus W pedantic minus O printf1 printf1.c. Well, it's only complaining about the fact that I'm not using the argument count, even though I'm passing it into main. And I did turn on a lot of warnings. Okay. So if I just run this program, printf1, hi, just prints hi. Okay, so this program seems to print its arguments, but it does so in the wrong way. That really should have been printf, and then the format string specifying that the first argument it gets should be printed as a string, and then give it the first argument. Now why? Well, we can make this program misbehave. What happens if we run it with a string, with an input that is a valid format string? What it will do is print the first argument of printf, even though no argument was there. And I can make it print even more if I do it as a pointer. And I can make it print even more if I say multiple pointers. So it's printing the subsequent arguments as instructed by the format string that I'm giving it on the command line, which gives me access to the stack memory. Now, this kind of attack has been known since 1989. Well, this property of printf has been known since 1989, but the first attack that broke something was actually only in 1999. Now remember, C is from 1972, so there were years and years before this was developed into an attack, but now that there are attacks, it is often abused. So this allows you to read data from the stack and the heap, and it's actually easy to spot. If there's no double quotation mark after printf, it's suspicious, right? But if we want a compiler warning from GCC, we need to use -w format equals 2, because why would you turn this on by default, right? It's not as though it's a huge security issue. Now the Clang compiler does report these by default, and this is just one more example of how legacy from the 70s should not be trusted for security. Now, why is this happening? Well, remember that according to the calling convention on x86-64, we put the return address on the stack, we optionally store the frame pointer, and then we put the first 6 arguments in registers, and then we put the remaining arguments on the stack, and we jump to the address of function. And the func in this case would be printf. Now, like I said, we don't have this frame pointer, but this is all machine code, and it doesn't care that the values in those registers weren't actually put there by earlier machine code preparing the function. So printf, while executing, will read these registers as though they were arguments to the function, even though these registers were not prepared by the call to printf. And it will, after hitting this seventh variable, it will start printing the stack itself. Now, again, why we put arguments in registers? Well, that is a lot of time waiting for memory saved. So I've already shown you printfp. We will just print this value of the second register that would contain an argument, and I can use this special syntax %7$p, and that then prints me the. Do I have a? The first 8 bytes on the stack might actually. Oh no, single quotation marks, because otherwise. There we go. So that's the first 8 bytes on the stack. So printf is a very powerful memory introspection tool. If I compile and run this this version, GCC. So this actually warns me about this unused variable here, 0x datcode cafe food. And if I run that version, with a lot of %p's, which I'm going to just generate automatically in a subshell because I'm lazy. Print %p space times 14. Oh, yeah, there we go. Thanks. Sometimes switching is hard. Okay, so going back to what I just said, let's run this once. So printf1 with %7$p will just print like this 8th value in memory. Now I've compiled this other version of printf, which warns me about this unused variable datcode cafe food, but it's in there. This datcode cafe food is somewhere on the stack. So if I now call that with 14%p's, so this code, what that does is, well, generate this string, and then if I call it like if I call it like this, that string gets passed to printf. So now I get 14 pointers to memory. And I see that indeed I print enough memory to see datcode cafe food. And I also see here the return value of printf. And if I were to print even more pointers, I would also see the return value of main here somewhere. But so the point is, we can inspect memory here, and we can do so quite reliably. Okay, so I have some additional code on these slides where I ask what's wrong with the code, and you answer, but seeing as we're out of time, left as an exercise for you at home. They are pretty pretty straightforward. So just look at why they are wrong, basically. So it's in 3 parts. Now, to find memory bugs, well, they are hard to find manually, but fortunately, there is assistance in the form of tools. Oh, I need to get better at switching between slides and code. Okay, so fortunately we have assistance in the form of tools. So what Valgrind does is basically run code in a sort of virtual machine. And the virtual machine basically checks all your memory accesses. Now that is of course much slower than actually running the code without these checks, but it finds memory leaks, so it finds some mallocs without free. It finds access to the freed memory. It finds double frees. It finds branches and memory access that depend on uninitialized data, so basically undefined behavior. And there are many more tools beyond the memory checker in Valgrind. For example, you have a cache profiler that looks at how the cache timings behave, and you have Callgrind, which generates call graphs. So there's a lot of tool assistance for runtime analysis of C code. Now, runtime analysis means these are dynamic analyzers, not static. Now, the type checker is an example of static analyzer. A dynamic analyzer doesn't give you any guarantees about branch coverage. If there is a branch that you only ever hit once in a blue moon, then Valgrind may never have seen that branch. And if you have memory leaks in that branch, Valgrind won't detect them. But generally, it's good practice to run your code in Valgrind before publishing it or submitting it somewhere, and making sure that Valgrind reports no errors. Nowadays, there is also libasam, the address sanitizer library, which you can compile into your code with -f sanitize is address, and then that will slow down your code because it's doing checks all the time, similar to Valgrind, but it will terminate when it finds bad behavior, and it will tell you the bad behavior. Now, there are also other sanitizers in libasam. It can find undefined memory. It can find basically other memory issues. It can find threading issues like deadlocks and stuff like that. And it can find memory leaks. Now, not all of these can be used together at the same time. Not all of them are useful by themselves. If you want to use this, consult the documentation. It has manual pages. It has good write-ups. So, to wrap up today, memory management is hard. The less the programmer has to do, the better. That is really a key takeaway here. Now, in C, we can manipulate memory quite freely, and this lecture and the assignment is basically preparing you for doing so in a controlled manner. Now, all this assumes you have an operating system and you have a C library doing memory management. But as we've seen in the case of the car, C is also used to program small embedded microcontrollers, and these give a lot less guarantees about memory. Sometimes it's even used to run on bare metal, so without an operating system. And because C is quite low level, you can do that. But it also means that you have no virtual memory. You have no segmentation faults. You are responsible for all the memory yourself. So in those cases, the stack can just happily grow into the heap or data segment without you noticing it. And typically these devices have rather little RAM, so this happens easily. That is really nasty debug behavior. So if you're an aspiring C programmer and you want to go into a sector that really has you program this kind of device, learn to code C properly and try not to kill anyone. So on that happy note, good luck on the assignment. I will see you Thursday next week. And I will take any remaining questions in chat now. Okay, could I please briefly explain again why printf prints from the memory if we give it a format string as an argument is not completely clear? Okay, sure. So we have a call. Let's say we have some C code. I'm going to put the format string in here. P. Let's make it P. Okay. So there's multiple things going on here. For one thing, C supports, and this is how printf is implemented, functions with a variable number of arguments. So printf with 1 argument, 2 arguments, 3 arguments are really the same code. And it cannot check at compile, well, it could check at compile time, but it doesn't, that this format string would actually require an argument to be given to the function. So what happens here is printf gets compiled down to some machine code. And that machine code basically says, I have to break printf down in its individual steps. So basically get format string. That is step 1. Get format string. 2. I'm going to ignore normal characters. 4. Each percent print next argument. That is how printf goes through its format string. Each percent it encounters, it just looks for the next argument to the function. Now, the way a function looks for its arguments is not dependent at all on how many arguments it actually got. So there's this calling convention that I said. So the first argument, we have these processor registers. Rex are bx, rcx, rdx, and then there's also r. So I'm not entirely sure. There is an R8X, I think, and an R7X. Like these, there's all these processor registers. And basically the first 6 variables, the first 6 arguments to any function call get put in those registers. So let's say that's 1, 2, 3, 4, 5, 6. We don't really care which they are. There are 6 register arguments go in there. And then the other arguments go, the other arguments actually they go before the return address on the stack. So the other arguments normally, argument 7, argument 8, etc., they get pushed to the stack, and then the return address gets pushed. And function variables happen here. So when printf gets a format string, it doesn't care that it was called without arguments. It will start going through this loop. It was just for this first %p, it gets the argument from this first register. Suppose it has %p 1, 2, 3, 4, 5, 6, 7, 8, 9, 10% p. Suppose that is the format string. Okay, then this first argument will get that. This first %p will get that argument. This 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 %p will get that argument. And then these start reading. Well, actually, I think it's the other way around. I'm not entirely sure about the calling convention right now. It might be this way around. So these start reading argument 7. This one gets this argument, and this one gets this argument, and this one gets, well, whatever is up there, right? There will be an arc9 and an arc10. That is how printf thinks the memory is laid out. printf is expecting all these arguments in all these places because that's what the format string is telling it to look for. And the contract of printf is that if you give it a format string with 10 arguments, you've actually called the function with 10 arguments. It is not printf that has to prepare all this for arguments. It is the caller of printf. It is the code that turns arguments into registers. That hasn't happened, and therefore when printf starts getting the arguments from the places it should get them normally, it actually starts writing out, well, the data that is in the place of where an argument would be if you had called printf correctly. So I think that should clear that up. Okay, good. Then I think I have to end it here because I also have to start preparing for the lecture Networks and Security. Yeah, so good luck on the assignment and see you Thursday next week.